Hello guys, welcome back to CFD College. I'm Ashkan, and in this video I'm going to solve some problems from chapter 2 of Fluid Mechanics 1 book written by Manson. And in this video we should solve some problems on fluid static where we have to find forces due to a column of liquid or mostly water acting on some gates. It's a bit difficult, maybe the most difficult part of the course, so you have to be careful, you have to pay attention to follow the steps and don't get confused. And before starting the video, please subscribe to the channel if you like these videos. If you are looking for a source for learning CFD and numerical simulation, as you can see in the channel, I have lots of videos on computational fluid dynamics using commercial software, and you can enjoy them. And also, if you like these videos and find them useful, please share them with your friends. Let's jump to the problems. These problems are part of assignment B of Fluid Mechanics 1 presented in Concordia University, but I think these problems are useful to anyone, to any person who's studying mechanical engineering. Okay, let's start. First, problem number 87 of chapter 2. We have a tank here which is 4 feet wide and homogeneous 4 feet wide. So in the third dimension, width, the width of the gate and these walls are 4 feet. 4 feet wide, 8 feet long rectangular gate. So this is a rectangular gate, the simplest type of gates, weighing 800 pounds. So we cannot neglect the weight of this gate. Is held in place by a horizontal flexible cable. This is the cable. Water acts against the gate, we know that, which is hinged at point A. So here we have a hinge. Friction in the hinge is negligible. It is always true in Fluid Mechanics 1. All the hinges are frictionless. Determine the tension in the cable. So we want to find this tension. If you know, when we have when we have a still water, due to the weight of water and hydrostatic pressure, there are some forces. And for example here on this gate, a force is acting on the gate due to water, and we want to calculate it. Here in this specific problem we have other forces. One is the gate weight. In most of the problems we neglect the weight of the gate and this tension on the cable. Let's talk about this phenomena, and then I will solve the problem for you. Imagine this is a gate, and here we have water. and this is the ground. As you know, here on the surface we have atmospheric pressure. So here if we work with gauge pressure, pressure is 0. And at the bottom, due to the column of liquid, the column of water, we have hydrostatic pressure. Pressure increases up to this value, and if it's H, you know that here the pressure is gamma H. So this is the pressure distribution. It's linear, and because of this pressure we will have a force, and since pressure is has a linear profile, this force acts here, not at the middle, a bit lower than the middle of the gate. So the acting point is somewhere here. This force has three characteristics. One is magnitude. Two is direction. And three, the third one, is acting point. And you should determine all these three characteristics. Direction is easy. This force, due to any liquid, is always normal to the gate and towards it. So if you have an inclined gate, for example this, the force is perpendicular to the gate. The magnitude is Fr is gamma HCA. Gamma is specific weight of the liquid, A is the area of the gate, and HC is the distance from the liquid free surface to the centroid of the gate. So it depends on the gate shape. Here we have a rectangular gate. We know that center of gravity is here, the centroid of the gate. So this is HC, and HC is a vertical distance. And acting point, you should find acting point as YR equals IXC YC times A plus YC. Imagine this gate incline. Here is the ground, and here is water surface. You should first locate the Y axis. This point is our origin, the intersection of the free surface and the gate, and you should place and locate Y axis here. So this is Y axis and Y direction. So when we say that YC, it means that here is the, for example, centroid or center of gravity of the gate. So this is YR. So this is YR. Why? We use this to find the acting point. This is FR and this distance is, sorry, this is YR. Oh, I'm really sorry. This is YR and this is YC. Here is the centroid, the center of gravity. Why? Really, why? Okay, I'm sorry. This is YC and this is YR. Now you know the difference. So you need to know YC to use it in this relationship formula and find YR. And these formulas are true for any type of gate. It doesn't matter whether it is rectangular or circular. And what is YC? YC is this. Oh, sorry, HC. This is HC. The vertical distance between the free surface and the centroid. So when you have this kind of gate, a rectangular vertical gate, since y axis is in this direction and here is HC, YC equals HC. So sometimes the students get confused. This is the reason, and it's an exception. It only happens when we have a vertical rectangular gate. Okay, I hope I explain it good for you and you know what should we do. Now, after solving these problems, you will understand it better. Okay, let's jump to the problem. In this problem, we know we have weight. So if this is the gate, here is the hinge, we have W, here is the centroid, we have T, the tension of the cable, and we have FR. So we want to find T and we know W, so let's calculate FR. To do that, here is the gate again, this is the cable and this is water surface, here is the hinge and this is the ground. So I should locate Y axis here. Here is the centroid, so this is HC, this is YC, and here is FR, so this distance is YR. Okay, now we can solve it. HC here is 3 feet. HC. This is 3 feet, and we know the angle. The angle here is 60 degrees. So we want to find HC. HC equals 3 feet times sine of 60. This is HC. If you see this, here is HC, here is 3 feet, and this angle is 60 degrees. So HC equals 3 feet sine of 60. This is HC. And as I told you, FR equals gamma HC area. So gamma is 62.4 pounds per cubic feet. HC is 3 feet. Oh, and you know, it's important. This part of the gate is important to find FR, to find HC, and to find YR. That's why I locate the y-axis here. So the part of the gate which is in contact with the water, that's only important. 3 feet times sine of 60 is HC, and area of the gate is 6 feet times 4 feet wide. So FR is 3,890 pounds. Now we know the direction, we know the magnitude, we should find acting point. Okay, we know that YR equals IXC YCA plus YC. IXC is usually given to you in the exams, so don't worry about it. YC equals 3 feet. So we know YC, we know A, and IXC. IXC for a rectangle is 1/12 B times H to the power 3. So if this is the gate, this is H, and in the third dimension we have B, the width. So YR equals 1/12. B is 4 feet. I'm sorry. H is 6 feet to the power 3. YC is 3 feet, and area is 4 feet times 6 feet times 4 feet. So plus YC, which is 3 feet, equals 4 feet. So when you have a rectangular gate, the acting point of FR, of the force, is 2/3 from the top, from the water surface, and 1/3 from the bottom. So I think you can use it without calculation. This is the water surface. Here is the, if you want to find the YR, it is 2/3 from the top. So here is 6 feet, 2/3 is 4 feet from the top, and 1 feet or 1/3 from the bottom. That's a rule of thumb, and as you can see, we can calculate it. So you can memorize it and use it. 2/3 from the top, 1/3 from the bottom. It doesn't matter whether the gate is inclined or vertical, but you can calculate it. It's not difficult. So now we know that here is 2 feet. And this is the hinge. Now we have to use the equilibrium. We know that the summation of the moments of these forces, T, W, and FR, should be 0 over the hinge. So summation of moments over O should be 0. We have 3 forces. This is the hinge W. This is the distance T. This is the distance for T, which is 8 sine of 60. For W is 4, 4, because the total height of the total length of the gate should be considered. This part also has the weight, so we should consider the total length of the gate. 4 times cosine of 60. Here we are calculating a vertical distance, but here it's horizontal distance. That's why we have cosine here. And we also have FR, and this distance is 2 feet. So the moment of W and FR are clockwise. The moment of T is counterclockwise. So T times 8 feet times sine of theta, which is 60, equals W times 4 feet times cosine of 60 plus FR times 2 feet. You know FR. And W is 800 pounds. FR is 3,890 pounds. And by solving this equation, you can find T, which is 1,350 pounds. As you can see, this was the first problem, so I had to explain the phenomena, explain the concept for you. In the next problems, we can proceed much faster. This is the second problem. Problem number 106 of chapter 2. An open tank has a vertical partition, and on one side contains gasoline with a density of 700 kilograms per cubic meter here. So this is our tank. Here we have gasoline, here we have water, and the depth of gasoline is 4 meters. As shown in the figure, a rectangular gate. This is a rectangular gate that is 4 meters high and 2 meters wide. So the depth in the third dimension is 2 meters W. And hinged at one end is located in the partition. So here we have hinge, and this is the rectangular gate. Water is slowly added to the empty side here of the tank. At what depth H will the gate start to open? So we need to find forces and solve this equation. The summation of moments at this hinge should be 0, because if it's not 0, it starts to open. Okay, so here we have a rectangular gate, and on both sides we have different fluids. So this is the bottom of the tank. Here is the hinge, and this is, sorry, I'm a terrible drawer, I know that, and I admit that. So this is the gate. Here we have gasoline. This is 4 meters, and here we have water with a depth of h. And we need to find forces. We know that here we have an FR W from due to the water, and on the right hand side we have FRG due to gasoline. So we need to find these forces and acting points of them, because we know that the direction is like this, normal to the gate and towards it. Okay, let's start with the right hand side, with this side. So if this is the gate and this is water level, here we have FRG. If you remember, we should put y-axis here. The middle is HC, the distance between the free surface and the middle. And in this case, because we have a vertical gate, HC equals YC. And we have this distance YR. And now you know that since it's a rectangular gate, YR equals 2/3 of the depth. So 2/3 times 4 meter. And this distance is 1/3 of the gasoline depth. FRG equals, you know that the magnitude is gamma of gasoline, HC of gasoline, times area of the gate, which is in contact with gasoline. So gamma of gasoline equals rho g. We know the density and the gravity. So 700 kilograms per cubic meter times gravity 9.81 meters per second square times HC, which is the middle, 4 divided by 2 meters, and the area of the gate 4 meters, the depth times width W 2 meters. So FRG equals 110 10 to the power 3 Newton, or 110 kilonewton. Let's examine the left hand side, the water side. This is the hinge, this is the water surface, here is H. We have FRW, and as you know, here the distance is 1/3 of H, and here is 2/3 times H. This is Y axis, the distance up to the centroid is YC equals HC because we have a vertical gate in this case, and it's 1 over 2 times H. Now you can find FRW. It equals gamma of water, HC of water, and area of the gate which is in contact with water. So water has the gamma of 9.8, 10 to the power 3 Newton per cubic meter. This is the gamma times HC times area, H times width, 2 meters. And so FRW equals 9.8, 10 to the power 3 H square. And now we know that the summation of moments over hinge should be 0. FRW produces clockwise moment, while FRG produces counterclockwise moment. So they are they are in the opposite direction. So FRW times 1 over 3H should be equal to FRG times 1/3 of 4 meters. And from this equation, because we know this one and this one, we can find H. H is 3.55 meters. Now, see, if you follow the steps, you can easily solve questions and problems. Next problem, which is a bit challenging. Problem number 110, chapter 2. Here we have a closed vessel of the figure below. The closed vessel of the figure below contains water with an air pressure of 10 psi at the water surface. So we have a closed tank, and as I mentioned in previous videos, when we have a closed tank or pressurized tank, we should know the pressure of the air here, which is the pressure at the water level. So we know it's 10 psi in this problem, and pay attention, it's not absolute, it's a gauge pressure because it's not psia. This problem is really important. One side of the vessel contains a spout that is closed by a 6-inch diameter circular gate. So this is the gate, 6-inch in diameter. So it's not a rectangular gate, it's a circular gate that is hinged along one side. Here we have the hinge or axis. The horizontal axis of the hinge is located at 10 feet below water surface. So this distance is 10 feet. Determine the minimum torque that must be applied at the hinge to hold the gate shut. Neglect the weight of the gate and friction at the hinge. As I told you, all the hinges are frictionless, and most of the time we neglect the gate weight. Okay, so let's see what we have. This is the gate, which is a circular one. Here is the hinge, and we have two different forces in this problem. One is Fr. You know that it's due to water. It's kind of, hydrostatic force, which is not acting on the centroid of the gate. You know why? Because we have a linear pressure profile, and you know that. But in this problem, we have air here, and air has a pressure on this surface. As I told you, when we have a gas, the pressure is the same and constant at any point. This air add another force here, Fa, for example, due to air. So because of this pressurized air here, another force will act on the gate, which is Fa. And since the pressure due to gases is the same and is constant, it doesn't vary with height, with depth, because the density is low, and we don't consider hydrostatic pressure for gases. That's why we put the force here, and this force due to air acts on the centroid of the gate. So this is force Fr is the force due to liquid, Fa is the force due to gas, which is air here. Now we can find the answer and solve the problem. Fa is easy to find. Pressure due to gases equals, the force due to any gas equals pressure times area. So air pressure times area of the gate. We know air pressure, which is 10 psi, and its gauge. So 10 pounds per inch square times 144 inches square over feet square times area of the gate, which is pi over 4 times diameter, which is in inch, so we should divide it by 12 to have feet square. 283 pounds. So once again, we have two forces, Fr and Fa. Fr is due to liquid, the hydrostatic pressure in the water. Fr is due to the pressurized air here. The acting point of Fr is YR. So we should calculate and find the acting point. But this force, Fr, which is due to air, acts on the centroid of the gate because it doesn't have any, distribution. It's the same. It's constant. Actually, if it's a gate, this is pressure of air. And as you can see, it's uniform. So it acts on the centroid. Okay, this was the easiest part. Let's find this force and the acting point. It's easy to find the magnitude. Fr, the formula, it's gamma hc area. Okay, now we have to find hc. This is the gate, and if I continue the direction, I reach the water surface. We know that this distance is 10 feet. And also we know the angle through this triangle. This is the hinge and this is 10 feet. So we want to find this distance because we can find this one using the triangle. 3, 4, here is 10 and this is 5. We can find it, but we should find y r actually, and we know that this force acts on this point. So first we need to find HC or YC actually, and then we can calculate YR. Here is the centroid, so we should find YC. YC is this. This is YC. Okay, let's find HC first and then we can find YC using the angle. So if I draw this is HC, and if we find HC we can easily find YC. So what is HC? Equals this 10 feet plus here we know that the radius of the gate is 3 inches, so plus 3 inches, and I divide it by 12 because I want feet, times the the angle. 3 is 3 to 5, and here we have 3, so I should multiply this by 3 over 5. Actually it's this 3, 5, and here we have 3. We want to find this. This is 3 times 3 over 5, this one. So HC equals 10.15 feet. Now we have HC. We can find FR. So FR equals gamma 62.4 pounds per cubic feet times HC 10.15 feet times area pi over 4 times 6 over 12 feet square. So FR equals 124 pounds. Now YR equals IXC over YC times A plus YC. We have HC and we can find YC. YC is this amount plus 3. So YC equals 10 feet times 5 over 3. See here we have 3 and 5, and 10 should be here, and we need this one. 5 times 10 divided by 3. 5 times divided by 3 plus the radius 3 over 12 feet. So YC equals 16.92 feet, and now we can find YR, sorry. So YR equals IXC pi over 4. You can find the formula in the table in the book, and times radius divided by 12 feet to the power 4. YC, we know that 16.92 feet times area pi over 4 times 6 over 12 feet square. So YR equals plus 16.92 feet, which is YC. So YR equals 16.92 feet. If you calculate this value, it's really small. It's I don't know, I think near 0.001. So we consider YR as 16.92. Now we have the magnitude of FR and FA and the distance of those forces to the hinge. Now we can solve the summation of moments over hinge should be 0. So this is the gate, this is the hinge, FA, and the distance we know it's 3 inches. FR, we know the distance, which is YR minus we know YR, but we should subtract this amount, I think 10 YR minus 10 times 5 over 3, and we need to find the force, the moment we need. So we should find this moment. So I consider the moment C here, and we should calculate it. So the moment produces by FR and FA are in the same direction, so we should add them together. FA times 3 over 12 feet plus FR times YR minus 10 multiplied by 3 over multiplied by 5 over 3 feet equals C. And I think you can do this yourself. C equals 283 pounds times 3 over 12 feet plus 124 pounds times 16.92 minus 50 over 3 feet. So C is equal to 102 feet pounds. This is the moment we need. It's a bit difficult, I know that, but the most difficulty I think is in finding the dimensions due to the angle. Let's see what we have. Okay, another problem. Problem number 117. In this problem, we have this system. Here we have water and a gate. The 18 feet long lightweight gate, this means that we don't need to consider the weight of the gate. Of the figure below is a quarter circle, so this is a quarter circle and it's hinged at H here. Determine the horizontal force P required to hold the gate in place. Neglect the friction and the hinge and the weight of the gate. Okay, now we need to find this force. So here we have, if we separate this section, two forces are acting on the gate. One is the weight of the water, and the other is the force due to hydrostatic pressure. So if we have this, then we have two forces, Fr and W. Okay, so let's at first start with Fr. As you know, Fr equals gamma HC times area of the gate. So this is the y-axis, and here, so if it's y-axis, we know that HC is at the middle. HC is 6 divided by 2 feet, and now we can calculate Fr, which is equal to gamma 62.4 pounds per cubic feet times HC 3 feet times area of the gate, which is a quarter circle. So the area of the gate, but we are calculating Fr. So in this way, we can assume the gate has this section. So the area of this section is 6 feet times the width, which is 18 feet, the width of the gate. So the area is 6 feet times 18 feet. Actually, in this problem, we have decomposed the force. If this is the gate and we have water, so the actual force is like this. This is the force, but we decomposed it into two parts: W, weight, and Fr. So W now is acting on this one, while Fr is acting on the vertical part. That's why we should use this area. So Fr can be found as 20,200 pounds. So this is Fr, and as you know, this distance is 2/3 from the top, so 2/3 times 6 feet, and this distance is 1/3 from the top. Times 6 feet. Okay, now let's deal with the W. This is the gate, and here is W. This distance, the distance between the center of gravity and the hinge, which is here, H, can be found from this formula: 4 times radius divided by 3 pi. Okay, now we have to calculate W. It's easy to find. The W is gamma of water times the volume of this section. So gamma is 62.4 pounds per cubic feet times the volume, which is the area of this quarter circle, multiplied by the width, for example B. Okay, pi over 4 d square, pi over 4 radius to the power 2 times the width, 18 feet. So W equals 31,800 pounds. Okay, now and this distance, for example, x1 equals 4 times r, 6 feet divided by 3 pi equals 8 over pi feet. Now we have the magnitude of the forces, W and Fr, and the distance between these forces and the hinge. Now we can find the force P by this equation. The summation of forces, the summation of moments over hinge should be 0 if we want to hold the gate in place. W produces clockwise moment, and also Fr clockwise moment, while P produces counterclockwise moment. So P times distance to the hinge, which is 6 feet, P times 6 feet equals W times 8 over pi feet plus Fr times 1/3 of 6 feet. So if you solve this, you can find P, and P is equal to 20,200 pounds. When it comes to these shapes, circle, quarter circle, or half circle, it's a bit challenging, so I recommend you to solve these problems yourself in order to find out what you should do at the exam. Okay, next problem. Is there any other problem? I think it should be another one. Okay, let me fix this issue and we can continue this video. Well, this is the problem I talked about, problem number 131. This is the most challenging problem in this assignment, so please pay attention to what I do to solve this problem. We have three different gates, A, B, and C, of negligible weight. So the weight of the gates can be neglected, are used to hold back water in a channel of width B. So the width of the channel in the third dimension is B. The force of the gate against the block, this is the block, for gate B is R. So this force is R. Determine in terms of R the force against the blocks for other two gates. Okay, so we should start from gate B and find R, and then we can solve for gates A and C and see how much R is the force against the block in those cases. Okay, let's start with gate B. So this is gate B. This is the gate. We have force R, and we have force due to the water Fr. Here is water surface, so I should put y-axis here, and this distance is yr. Here at the middle we have hc, which is equal to yc in this case because we have a vertical gate. Okay, it's not difficult for you, I know that. Fr equals gamma hc and the area. You know, hc is, since it's a rectangular gate, and okay, if this is the ground, the depth is h. So hc equals h over 2, half of the h, so gamma times half of the h times area, which is h times b, the width. So Fr equals gamma h square b over 2. And since it's a rectangular gate, you know yr equals 2/3 of h from the top. You can also find it, but as you know, yr equals ixc, if I'm not mistaken, over yca plus yc. But for rectangular gates, you know that it's a 2/3 of the depth from the top and 1/3 from the bottom. Okay, now we have to look at the hinge is here. Now we have to solve this equation, the summation of moments over h equals 0. We have two forces, Fr times yr equals r times h. So gamma h square b over 2 times y, this is r, sorry, yr, which is 2/3 of h, equals r times h. So r equals gamma h square b over 3. Now we know r. Now we have to solve other cases and compare those forces to r. So let's start with a case A, this case. Okay, here the gate is like this. We have a quarter circle, and this vertical part here is this ground, and this is the water surface. The radius here is hinge. The radius of this circle is h over 2, and this distance is h over 2. Okay, to solve this, we have three actually different ways. One is to consider two forces for this quarter circle: horizontal force, vertical force, and then consider Fr for this part, for only this part, the vertical part. The other option is to consider this force Fr1, for example, for the circular part, and Fr2 for the vertical part. Or the third solution, which is, you can consider Fr for both vertical parts. So this is the vertical part, and you can consider this part, vertical part, and in this Fr you are considering both these forces, Fr and Fh. So in this force, you are considering the horizontal and Fr. So let me name it Fr prime. Fr and this, and consider vertical force for the circular part. This is what I'm going to do according to the solution manual. Okay, so we move on with the third method. So it seems that we have this gate. Here is Fr, depth is h, so it's pretty similar to what we have solved in the previous section, part B, yes, gate B. It's pretty similar. You know that Fr equals gamma HCA, and HC equals h over 2, and yr equals 2/3 of h. As I mentioned, it's similar to what we have done in this part. So Fr equals gamma h square b divided by 2, and we know yr equals 2/3 of h. And for the circular part, we have this one. Here the vertical force is due to the weight of this liquid, the liquid here. You can find the force easily because it's a quarter circle, so W, the weight, equals gamma times volume, gamma times volume, which is the area of this part times the width divided by 4. So pi times radius to the power 2, this is pi r square, which is the area of a full circle, divided by 4, the area of this quarter circle, times width. So the weight equals pi gamma h square b over 16. And if you know that the distance between the force and the origin and center of the circle is 4r divided by 3 pi. So now we have our forces. So we have this system, we have Fr, and we know Yr, and we have W, and we know this distance. But remember, pinch is here, hinge is here, so we need to know this distance, which is h over 2, the radius, minus 4r divided by 3 pi, 4 times h over 2 over 3 pi equals 4h over 6 pi. So here is h over 2 minus 4h over 6 pi. Now we can solve the moment equation. The summation of moment over inch should be 0. So the moment, and here you know that we have this force. For example, Fb. So Fb times h, the distance, equals Fr times Yr, which is 2/3 of h, plus W times h over 2 minus 4h over 6 pi. And now if you solve this, you will end up with Fb equals gamma h square b times 0.39. So Fb equals 1.17 r, because we know r is gamma h2 times b over 3. If you divide this value by that, you will end up with this one. And now gate C. Okay, gate C is like this. So we have this gate. This is the surface of the water. Here is the ground. This is hinge. And we know here we have FB. And we have to find other forces. What do we have? For this circular part, we know that the force, sorry, let me clean here. This force passes through the hinge, which is the center of the circle. So when you want to calculate the moment of the force of this F, you should multiply the F by 0. So this force doesn't create any moment. So we don't need to consider that. If you see here, I told you that this force passes through the circle's center, but in this case the hinge was here, and this force creates a moment over H, over hinge. This is why in the gate A we should consider this force, and in gate C we don't need to consider this force. And it's like what I mentioned here. We have different ways. Since we consider force in this way, you know, the force which is passed through the circle center, we are in this method. So we need to find the force acting on this part only. So this is the difference. In this case, we consider the vertical part from the top up to the bottom and solve the vertical force on the circular part. But here, the circular, this force, you know, the horizontal part of the force is included in this force, in this one. And we do not, and we should not, actually it's better, we should not you know, consider the horizontal force acting on the circular part. So we have only this part. So it seems that we are facing this situation. This is the bottom, this is the gate on which we have to find the force, and here is water surface. So as I mentioned before, place the y-axis at the intersection of the gate and the free surface. So this is y-axis, and it should be parallel to the gate. So this is y-axis. Here we have FR. Here we have let me draw better. This is FR, this is FB, here is the middle, so this distance is YC equals HC. So YC equals, HC equals H over 2, the radius of the circle, plus H over 4, because the total height of the gate is H over 2, plus H over 4 equals 3 over 4H. And we need to find YR, this distance. YR equals YC plus IXC over YC times area. So YC is 3H over 4 plus 1 over 12 width times the height of the gate, H over 2 to the power 3. And in the denominator we have 3H over 4 times the area of the gate, which is H over 2 times B. So YR equals 28H over 36. Now we have YC and YR. We can calculate FR, gamma HC area, gamma 3H over 4, and the area H over 2 times B. So FR equals 3 over 8 gamma H square times B. And now we can solve the moment equation. The summation of moments should be 0. So FB times H equals FR 3 over 8 gamma H square B times YR, which is 28H divided by 36. So from this equation you can find FB equals 7 over 24 gamma H2B, and if you divide this by R you can find that FB in this case in gate C equals 0.875 R. See, this is the most difficult problem in this assignment and probably in this chapter. And we have another problem related to buoyancy force. Problem number 145, which is related to buoyancy force. When a hydrometer having a stem diameter of 0.3 inches is placed in water, the stem protrudes 3.15 inches above the water surface. So we have this height. If water is replaced with a liquid having a specific gravity of 1.1, so Sg of the liquid is 1.1, meaning that gamma of this liquid, for example gamma L equals 1.1 gamma of water. How much of the stem would protrude above the liquid surface? The hydrometer weighs 0.042 pounds. In these systems, when you have an object inside any liquid, we have two forces, especially when we have equilibrium. I mean, the object is steady and still in the liquid. One is weight of the object, and the other force is buoyancy force, which is always upward. Buoyancy force, Fb, equals gamma of the liquid. It's important. Gamma of the liquid, gamma of liquid times volume of the object, which is inside and within the water. Okay, so here we have equilibrium, so summation of forces in vertical direction equals 0, so W should be equal to buoyancy force. In both situations, so when we have water, W equals buoyancy force, gamma of water times volume, for example V1, and when we have a liquid, an unknown liquid, the W equals gamma of liquid times V2, gamma of L, equals 1.1, or Sg Sg gamma of water times V2. Since the weight is constant, the weight of the object, because it's the weight of the object, not the part which is inside the water. So gamma of water times V1 equals Sg gamma of water V2. So from this we can understand that, we can find that V2 equals V1 divided by Sg. We know the weight of the object. So for example, for first situation where we have water, we can find V1. So the first situation where we have water, V1, the volume, equals W divided by gamma of water from this equation. So we know the volume, the weight, 0.042 pounds per gamma, which is 62.4 pounds per cubic feet. So V1 equals 6.73 times 10 to the minus 4 cubic feet. And we can find V2 now. We know V2 equals V1 over Sg, V1 over 1.1, so V2 equals 6.12, 10 to the power minus 4 cubic feet. Now we can find the difference. V1 minus V2 equals 0.61 10 to the power of minus 4 cubic feet. And now we can find the difference in submerged depths. So this difference, this volume difference, equals the area, the volume of the volume of this part, which is equal to area times delta L. So equals area of a circle is pi over 4 times diameter square, which is 0.3 inches square times delta L. It's equal to this value, 0.6 10 to the minus 4 cubic feet. And since on the left hand side we have inches, we should convert the right hand side. Every 1728 cubic inch equals 1 cubic feet. So from this you can find the delta L equals 1.49 inches. So in the first situation, we had this height above the water surface. So in the second situation, for example, L2 equals 3.15 inches plus 1.49 inches equals 4.64 inches above the surface. This is how you should solve this problem. It's easy. It's not difficult. Thank you for being with us. If you like these videos, please share them. We have lots of other videos in this channel related to CFD, numerical simulation, ANSYS Fluent, and so on. So you can enjoy them as well. And again, thank you for watching this video. Please subscribe the channel, and until the next video, take care of yourselves and bye bye.